since today we are going to deal with a microscopic theory, I start right away with the Hamiltonian. So the Hamiltonian which we are going to discuss today is given by very simple form. It's sum over n not equal to m, which means that there is a sum of n, m, and n not equal to m. Some coupling constants g and m, s n dot s n. So this is a simple model. Well, for generality, I will add interaction of a spin sum over n, s, n, z. So this is external magnetic field. For everything what I'm going to tell today, H external will be denoted as H. However, the first part of my lecture will be related to discussion of the model in the absence of this topic. So, what it is here? So we consider a lattice of atoms which D or F shell is not completely filled, and therefore, according to Hund's rule, there is a local spin associated with each atom in the lattice. And these spins are talking to each other through the interaction, which depends, of course, on the relative distance. And m is j, which depends on modulus n minus m. So sometimes in my lecture, almost all the time, I will have a shortcut notation, R. This is Rn, and M is Rn. This is the numerated position of the spins. The interaction between spins can be as long-range interaction, for example, due to magnetic dipole interaction, or it can be short-range interaction. Again, for most of my lecture, I will not specify what is G and M. However, to complete the story, I mean, to do some exercise, at some point, I will consider that the interaction is among nearest neighbors, which is quite understandable because what happens, you have an overlap of your well-paid functions, so you have exponential tails, and therefore, typically, the interaction indeed includes only next neighbors or sometimes next to next near neighbors. This is a realistic way to consider the Heisenberg model. However, it can also happen that due to Ruderman-Kittel-Kossou interaction, RKQY interaction, which we know results as 1 over R cubed dependence, the same way as magnetic dipole interaction, it can also be long range. It doesn't exclude this thing. There are different mechanisms of interaction between spins. However, the most common one, as I said, typically results in the interaction between nearest neighbors. Then, since I told you that in the title of my lecture, it's a theory of local ferromagnetism, I will consider that all exchange integrals, G and M, are positive, which means that ordering spins parallel each other, which happens, as we know, through the phenomenological models happening at temperature much lower than Tc. We will see also what Tc is. So, since all exchange integrals are positive, it means that ordering spins parallel to each other will minimize the energy, because the scalar product is then 1, and you have minimal energy corresponding to this ordering. Okay, let's do several exercises to rewrite this Hamiltonian in some way convenient for the discussion. So, for the first part of my lecture, I will consider behavior of ferromagnets at temperatures where low compared to critical. In the second part of the lecture, I will consider temperature higher than the critical. Okay, first of all, Sxn, Sxm plus Syn, Sym. As usual, we separate the transverse part. This is a transverse part, and longitudinal part, which is ZZ. And separation to transverse and longitudinal is due to magnetic field. As I said, I assume from the very beginning that there is infinitely small magnetic field applied to the system. I choose direction of my z-axis along the direction of magnetic field. The generator of the SU2 group, which we call SZ, is diagonal in this presentation, and this is off-diagonal path. So everything which is perpendicular to direction of the axis along magnetic field is transverse. Everything which is parallel is longitudinal. So I would like to introduce raising and lowering operator on the side, every side, such a way that this is Sx plus minus, let me put indexes, Sy, n, n. And there is I here. Okay. From quantum mechanics, you know that this is a raising and lowering operator. Sometimes they're called lead operator. If you need to refresh it, go to your course of advanced quantum mechanics and see what you learned about strings. If we re-express x and y in terms of s plus and the minus operator, we say that s and x is s plus plus s minus over 2, and s and y is s plus minus s minus over 2i. N. If I plug it here, because I want to re-express the transverse part in terms of raising and lowering operator, I get 1/4. Here, s plus n plus s minus n, s plus n minus s minus n. Then I have I square, which gives me -1, minus 1/4, s plus n minus s minus 2, s plus n minus s minus n. Okay, you see the terms like that or like that. There is plus here, will be cancelled out because there is a term like this and there is a term like that. And the terms which contain plus and minus will be doubled. Therefore, I have 1/2 s plus n s minus n plus s minus n s plus n. So we have a raising and lowering operator. Good. Let me postpone discussion of the transverse part for the next 10-15 minutes. What I also need to do now is to define a Fourier transform. For the first part of my lecture, I will take the Fourier transform in the following way. S plus n minus is equal to 1 over square root of n, sum over q, s plus minus q, e to the power plus minus I q r. What is unusual here? I define the Fourier transform for plus component with exponent plus, and Fourier transform for minus component with exponent minus. It's a matter of convenience for what I'm going to say. Also, I use symmetrical normalization, so s plus minus q inverse Fourier transformation will be 1 over square root of n, sum of n, s plus minus n, e to the power minus plus I q r n. So you see, whatever I do, I respect the rules for Fourier transform. If the direct one comes with a plus, the inverse comes with a minus. And as I said, I use symmetric normalization to the number of spins. In the second part, just to show you that in the literature sometimes people do it differently, I will use another rule for the Fourier transform. And one of the problems which I give you for non-mandatory consideration is to take this Fourier transform for the second part and take the Fourier transform which I will give you in the second part for the first part and see both derivations that everything is consistent. As I said, I do it deliberately because I want to show you that sometimes in the literature people use different conventions. So this is a convention number one. Good. Now let's write down the Hamiltonian in the Fourier transform form. Here. For the moment, I will keep this one, and we write. First of all, I will write it as a sum over n, m not equal to n, g and m. Look, I have term transverse Sn, Sm, Sn, Sm. So I can actually change notations n and m here. And since these operators since these operators commute on being on a different sides, and here I have explicitly conditioned that I have a different sides, without losing generality, I can write Sn minus Sm plus Snz Smz. Once again, this is transverse part, this is longitudinal part. Okay? You understand what I did? So in the first term, I just renamed n as m and m as n, and I commuted because spin operators commute being taken on a different sides. Okay. Now, with the Fourier transform, I keep the rules of Fourier transform here. So I will rewrite my Hamiltonian first considering transverse part. So this is minus sum over n, m, g, and m. Then there is 1 over n, sum over q1, q2, s minus q1, s plus q2, and then it's e to the power minus I qn plus I qm. Again, I use the shortcut notations that Rn is called n and Rm is called m. Okay, I will use the fact that this depends on modulus over n minus n, and therefore I will introduce vector n, which is precisely n minus m, and therefore m or n is equal to L plus m. If I plug it here and here, so I have a sum over m, sum over q1, q2. I reshuffle my summations. I have sum over m, and I have sum over L, and I have G, which depends on the modulus L, SQ1 minus SQ2 plus times exponent to the power minus I Q1. I will write it as L plus M plus I Q2M. Okay, so in this exponent, I don't need Fourier transform anymore. In this Fourier exponent, just let's look at the exponent. It is exponent to the power I M Q2 minus Q1 minus I Q1 L. When I take summation over M, sum over exponent with a radius vector Rm gives me n times, what I forgot to write 1 over m. Sum over m e to the power I m q1 minus q2 gives me n delta symbol Kronecker q1, q2. Therefore, my Hamiltonian, I will continue here, is equal to minus sum over q s minus q s plus q, and then there is sum over L, g which depends on modulus L, times I minus I q L. Okay, so I will denote this quantity as j q. Okay, good. Now I need to do something with the transverse part. Let me write down the transverse part, but before doing that, let me come back to commutation relations. Let me come back to the commutation relations. This is important. Good. So the logic, what I'm going to do, why I need to make detour to the commutation relations, because it's very tempting to introduce bosonic operators. And this is what I will do using so-called Holstein-Primakov representation. But before doing it, I need to remind you something about spin algebra. So the commutator S plus N M S minus N is equal to 2 times S N Z delta N. As I said, spins plus and minus components commute when n and m are taken on the different sides, and they form so-called Lie algebra of SU2 group. So the commutator S plus and S minus is expressed in terms of SZ. Therefore, in principle, spins are neither fermions nor bosons, because for bosons we have a commutator equal to 1. For fermions we have anti-commutator equal to 1. But here, the commutator of 2 ladder operators is expressed in terms of longitudinal component. Okay, if I take Fourier transform, I have S plus Q1, S minus Q2, minus S minus Q2, S plus Q1. And this is equal, because I want to write the same commutational relations in the moment in space. It's equal 1 over n, sum over n m, s n s m plus s n minus minus s m minus s m plus times exponent to the power minus I Q1 n plus I Q2 n. Okay, so if I plug in this commutator, I have 1 over n, sum over n, because I have a chronicle symbol, s n z, e to the power I n q2 minus q1. Good. What I'm going to use in my calculations, that if I'm at very low temperature, then all spins are arranged parallel to each other. This is the ground state, ferromagnetic state. Then at temperature equal to zero, I can replace all S and Z by S. So this is S divided by N, and I have a delta symbol chronicle Q1, Q2 times N.
Hello?
Yes?
Shouldn't you have factor 2 in front of the summation?
No, there is y factor. Sorry. There is factor 2. Yeah, that's done. That's important. Thank you. Yeah, there is a factor of 2. If, however, I'm not at zero temperature, I can do sort of mean field treatment and replace it by 2SZ average, which will be sort of average magnetization divided by n times delta symbol Q1, Q2. Yeah. So suppose I'm at very, very low temperature. Therefore, what I see here, that the commutation relation S plus Q1 S minus Q2 commutator is equal to 2S delta Q1 Q2. Again, provided that I am at zero temperature. Therefore, I can introduce bosonic operators. They are almost bosons with a proper normalization. So if I say that my operator S plus Q is equal to square root over 2S creation annihilation operator BQ, and S minus Q is equal to square root over 2S BQ dagger, then I can rewrite this commutation relation as BQ1 BQ2 dagger is equal to delta Q1 Q2. So you see there is sort of an approximation because I replaced the commutator either its value at the ground state or some average mean field value. However, apart of that, I see that my transverse component behave like oscillator, harmonic oscillator. So I already have term which is proportional BQ dagger BQ. Okay.
Excuse me, sir. Hello, sir.
Yes.
Okay.
Yes.
The second expression where you have C goes to 0, that is C equal to 0, you have to as no, the left hand side.
I don't understand what you're asking. If I have speed equal to what?
Okay, at the limit when the temperature goes to 0, we have 2S over n times n and then the Dirac delta. Now, the other part of it, at what limit is it? Where you have T 2 times the average of SZ divided by n. At what limit?
I said that if I'm at zero temperature, then this is exact, right? And
okay.
for what I'm going to derive now, I would like to confine myself to 0 temperature. Then I use just value of spin 1/2 or whatever. If, however, I'm at finite temperature, I can, in principle, put average here. And in the same level of normalization, I'm fine. I can still introduce bosons with this trick. However, this trick, as I said, becomes exact only at 0 temperature.
Okay, I see.
Then I don't need any min field because I'm at the ground state, and in the ground state, all spins are aligned parallel to each other. Good. So I'm done with the transverse part. You see that with the transverse part, this Hamiltonian will be written.
Hello, Professor?
Yes.
Sorry, I want to ask a question. So you introduce the creation and annihilation operator for in the place of the spin operators, like you make them like bosons.
Yes.
So
I think the reason why I'm doing that.
Is this like the? I mean, I read a term in the internet called bosonization. Is this exactly what you're doing?
It's all the trick. As I said, the problem is that spins in general are neither fermions nor bosons. Therefore, whatever representation you use for spins, it should, whatever representation in terms of fermions or bosons you use, this representation will not be fully correct. So there is a price which you are going to pay for this representation. In particular, I'm giving you an example when I introduce bosonic representation of the transverse component. And the price which I pay for it is non-exactness of this relation at final temperature. I need to use some method. Equally, I can use fermionic representation. I can express spins in terms of Majorana fermions or whatever. This has nothing to do with the bosonization. Bosonization is actually, you have one-dimensional system. Typically, bosonization is considered a one-dimensional system. And in one-dimensional system, fermions are not correct excitations, because I told you, in order to define correct excitations, one needs to consider the energy and inverse lifetime, and if they are comparable, and this is what happens in the one-dimensional situation, you cannot use fermionic language. However, it appeared that instead of fermions, you can introduce bosons related to the density operators, like phonons. And this is roughly bosonization. Of course, for spin systems, you can, if your Hamiltonian contains some spin density interaction, you can use so-called abelian bosonization or non-abelian bosonization. But this, as I said, is applicable mostly to one-dimensional system, as long as I'm talking about operator bosonization. Of course, for experts, I can tell you that you can use in the path integral some Hubbard-Satonovich trick, therefore you replace some combination of fermionic operator by bosonic field. You can also do it in abelian and non-abelian way, and this is so-called functional bosonization. It's not restricted by any dimensions, but as long as we are talking about exact or asymptotically results, bosonization works well for one-dimensional systems. Here, without losing any generality, I'm talking about three-dimensional system, and I will come to discussion of dimensionality a bit later. So it's just spin algebra, nothing else. And this is Hallstein-Primakov, by the way. This is trick introduced in 1940. Good. So what I'm saying is that I rewrite this part as 2s sum over q, g, q, b, target q, b, q. So transverse part is already written as quadratic form in the right way of harmonic oscillator. Okay, so now I'm going to massage the longitudinal part. And for longitudinal part, I again need to use the spin algebra. Let's remember, so there is sign minus, which is important. This is transverse part. So don't worry, if you have a problem with understanding of this trick, on Wednesday I will repeat, well, I will use the same spirit of derivation for antiferromagnetic case. Antiferromagnetic case, when you have two sublattices. Luckily for ferromagnetic case, in 5 minutes or 10 minutes, I will derive your Hamiltonian, which is already quadratic. And the form is quadratic form, which is already diagonal. For what we are going to do on Wednesday, for two sublattices, you will see that with the same level of trick, you will get, at the end of the day, the Hamiltonian, which is quadratic, but not diagonal, and I will use Bogoliubov transformation in order to diagonalize it. So today is a simple job. I will get everything almost for free. On Wednesday, we will repeat some part of the calculation for more complicated case, but we will need some extra step of diagonalization, so we repeat how the Bogoliubov transformation works for spin. So the idea for expressing S and Z, so remember that I have H parallel, which is minus sum over N and G and M, S and Z, S, M, Z. So the goal is to express S, M, Z and S, M, Z in terms of the same creation and annihilation operators of the bosons. How can we do it? So let's recall that S and Z squared plus S and X squared plus S and Y squared, which is S squared, is equal to S plus 1. Okay? Then S and X squared plus S and Y squared is equal to 1/2. S n plus S n minus plus S n minus S n plus. Right? So far we are doing exact things. So now I take a Fourier transform. So this is 1 over n. There is a factor of 2. Sum over q1, q2. S plus q1, S minus q2. Plus S minus q2, S plus q1. I have exponent I q1 minus q2 n. Or from the commutation relations which obtained here, this is 2s divided by 2n. Therefore, this is s over n. And I have sum over q1, q2, b q1, b target q2, plus b dagger q2, b q1, and I have exponent I q1 minus q2 n. So from the commutation relations written here, I can re-express this as delta q1 q2 plus b dagger q2 b q1. So in the first summed when I take the delta function. The delta function means that exponent has argument equal to 0. I have sum over q, and sum over q gives me the number of spins, namely n. So the first term, therefore, gives me s. The second term gives me 2s over n, because this term and this term is doubled. Sum over q1, q2, b dagger q2, b q1, e to the power I q1 minus q2 times n. Therefore, I can write down S n z square is equal to S times S plus 1 minus this part. So minus S minus 2s of n sum over q1, q2, b dagger q2, b q1, e to the power I q1 minus q2 n. You see that this is s squared plus s minus s cancels out. Now I need to take the square root. So s n z is a square root over s squared minus something. And this is sort of density operator. We will see that it's related to density of magnons. If this density is sufficiently low, I can Taylor expand the square root. I remind you that 1 minus x is approximately equal to 1 minus x half, plus and so on and so forth. And this is what I'm going to do, and therefore I first of all write down that S and Z is approximately equal to. So this is exact equal to S squared square root 1 minus 2 over S n sum over q1, q2, b dagger q2, b q1 e to the power I q1 minus q2 n. Then I expand the square root. So this is s. Sorry, I took square root over s squared. This is s times square root 1 minus, and s is here. So this is then approximately equal to s minus 1 over n sum over q1, q2, b dagger q2, b q1 e to the power I q1 minus q2 times n. Good.
Hello?
Yes.
Hello? Professor, earlier
Yes.
you defined the case between finite temperature and T equal to 0. Is this the case for T equal to 0? That
For the moment, it doesn't matter because I did not replace anything by average. The discussion about zero or non-zero temperature was relevant when I defined, when I introduced bosons. Here, I just use the fact that spin is sufficiently large. I can do sort of one over S expansion. This is one way. Because you see that this term is inversely proportional to S. In principle, legitimate approximation, as I said, consider S is large. Then I can do Taylor expansion without any further assumptions. But nothing about temperature here. Okay,
Um, can I have another question, please?
Yes.
So you're assuming in this system that S is large. What if S is like half that the system that we encounter usually, or that is there possibility? I don't know.
Well, in principle, this is a very good question. In all these theories, what I'm presenting now is rigorously correct if spin is large or the coordination number, namely the number of nearest neighbors, is large, then it's sort of 1 over S or 1 over Z inverse number of coordination number expansion. However, it appears that this representation, because as I said, this is sort of density of magnons, works well even for spin equal to 1/2. This is a big surprise, but rigorously, this expansion is not correct for spin equal to 1/2. But if you do it and you compare the results of magnon spectrum, which I'm going to derive with experimental measurement, you still have good quantitative agreement. However, as I said, to be on a rigorous side, the legitimate way to do it is either for large spin or large coordination number. For the simple cubic lattice, coordination number is 1/6. So 1 over 6 is good small parameter. The real expansion is in terms of 1 over 2s. If spin is equal to 1/2, 1 over 2 times 1/2 is 1. 1 is not small parameter. However, as I said, it works fine also for spin 1/2. Good. So let me write down the last step. Namely, on equal footing, I need to write the longitudinal Hamiltonian. So H parallel is, as I said, minus sum over n, m, g, n, m, s, n, z, s, n, z. So I will plug in what I obtained here. This is minus. I will write approximately because I already dropped terms of the order b dagger b square, which will be responsible for magnon-magnon interaction. So I dropped this term. So therefore, whatever I write for the longitudinal Hamiltonian is approximate. This is sum over n, m, g, and m, and this is s minus 1 over n, sum over q1, q2, b dagger q2, b q1, e to the power I q1 minus q2 times n, times the same bracket s minus 1 over n. Here I will take index summations q4, q3, and q4, b dagger q3, 4, b q3, e to the power I q3 minus q4 n. Let me open the brackets. I will continue it here. So H parallel is equal to, first of all, there is a term s squared. This sum is a sum of all sides, sum of the L, where L defines the number of nearest neighbors. Let me assume that only nearest spins interact, and therefore the sum of the nearest neighbors give you coordination number z. So z is coordination number. We'll see some example. So then the first term gives me minus s squared times n number of sides times z number nearest neighbors times G. I assume that G n m is equal to G if n minus m is equal to lattice constant A and 0 otherwise. Okay, this is the first term. Then I have 2 times terms which contain B dagger B. Therefore, it is plus 2 times S over N, sum over Q1, Q2, because these are indexes of summation. B dagger Q2, B Q1, e to the power I Q1 minus Q2 times N. And this is, of course, summation over N, M, N, and L. And then there is again term which is proportional to B dagger B squared, which again describes the interaction of modules. I will drop this term again. So the summation of, and there is GL. What I forgot. So the summation of n gives me n times delta function. So then the Hamiltonian is approximately equal. I will write it in node plus 2s. I have just wait. In the summation over n gives me n, so n is cancelled out, that this is 2s. Summation over L gives me coordination number z, and then I have j, and I have sum over q, b dagger q, b. Okay. We have 2 terms, this one and this one. Oh, both terms are already diagonal. Let me rewrite these 2 terms in very similar way, introduce something which is called structure factor. So namely, I would rewrite this term as minus 2sj z times sum over q, gamma q, b dagger q, b q. Therefore, gamma q is equal to 1 over z, sum over L, g depending on modulus L, e to the power minus I u L. Since I consider interaction only of the nearest neighbors, let me see how this gamma q looks like for simple cubic lattice. So this is so-called structure factor. After collecting these 2 terms, what I get, that my Heisenberg Hamiltonian, I will write it here. My Heisenberg Hamiltonian H, which is H parallel plus H perpendicular, is equal to E node plus 2 times S Z J sum over Q 1 minus gamma Q B dagger Q B Q. Where?
Sorry, Professor.
Let me finish sentence, and then I answer your question.
Okay.
Because I cannot answer the question before I complete the equation. So, E naught is equal to minus S squared NZJ, and I will denote epsilon Q is equal to 1 minus gamma Q. And gamma Q is 1 over Z, sum over L, nearest neighbors, G, L, e to the power minus I, U, L. Okay, your question.
Okay. It's about when you wrote H parallel in terms of Q1, 2, 3, and 4, and then you wrote it in terms of Z, and I didn't get that one.
Well, I have two brackets. Each of them contains S minus sum over Q1 and Q2. The second bracket, S minus sum over Q3, Q4. So now I take the product. The first term is S squared. The second term, so this is S minus 1 over N sum times S minus 1 over N sum. So when I multiply this by this, it's equal to S squared. Now I multiply this by that and this by that. It gives me 2 times over N and sum. This is the same. Q1 and Q2, Q3 and Q4 are index of summation because this sum comes twice. And then I have plus 1 over N squared sum squared. So this is how I open the bracket. I draw this term because it describes me the interaction between magnons. And I keep only these two. And this is what I got. Because here, as I said, Q1, Q2, Q3, Q4 are indexes of summations. I can take any indexes of summation because I'm summing about that. So therefore, the sum is doubled. Just product of two terms, nothing more than that.
Okay, thank you.
Okay, now let's consider some particular example. Because what I did, I took Heisenberg model in the absence of magnetic field. And under certain approximation, and I told you about my approximations at each and every stage. Namely, I took very low temperature compared to critical one. I take large spin limit. After adopting these approximations, I managed to write down approximately my Hamiltonian in the form of harmonic oscillators. Let's now consider example, simple cubic lattice. Let's take this particular spin. So this is side N. Next neighbors, this one, this one, this one. So 3, and there are 3 other. There is this one, there is this one, and there is this one. So simple cubic lattice. Z is equal to 6. Then I'm saying that for all neighbors, G and M is equal to J. Therefore, gamma Q is equal to 1 over 6 by the definition. Then it's equal to J because all J's are the same. And now I have e to the power I Q X A plus e to the power minus I Q X A plus e to the power I Q Y A plus e to the power minus I Q Y A plus e to the power I Q Z ZA plus e to the power minus I Q ZA. By the definition, this is X, this is Y, this is Z. So therefore, this is 2 times cosine QXA, this is 2 times cosine QYA, and this is 2 times cosine QZA. I have 1 over 6 times 2 times J. I have a cosine QXA plus cosine QYA plus cosine QZA. So this is a structure factor for the nearest neighbors. Let me take next to nearest neighbors. This is sort of the homework which I gave to you on a square lattice, if I remember well. Then you will get different structure factor. Take different symmetries of Bravais lattices, compute structure factors, assuming, for example, that you have nearest neighbors or next to nearest neighbors. This is for simple cube. What is important for me? Let me take limit q goes to 0. Then this is 1/3. Sorry, yeah. Oh, I took actually, sorry. In this definition, I need to divide by j. Therefore, j, of course, is gone. Because I already took j out, you see here. And of course, I'm writing 1 and some dimensionless function. This is dimensionless function. So this is 1/3. I expand cosine. So this is 1 plus 1 plus 1. It's 3 minus qxa squared over 2 minus qya squared over 2 minus qza squared over 2. This is equal to 1 minus 1 over 6 a squared qx squared plus qy squared plus qz squared. So this is equal to 1 minus a squared q squared over 6. Okay, so therefore, if we look at our dispersion, I will put this multiply because I would like to have dispersion having some dimension. 2SZJ times. So dispersion epsilon q goes to 0 is equal to 2 times SZJ times 1 minus 1 minus q squared a squared over 6. So it is equal to lambda times q squared, where lambda is equal to 1/3 SZJ a squared. So what we have obtained that we have new excitations, bosonic excitations. We call them magnons. Since this B and B dagger are originating for raising and lowering operator, which I remind you that S plus acting to state down transversal to state up, and S minus acting to state up transversal to state down. Therefore, this operator at the same time are corresponding to spin flip. This is for spin 1/2. If you have spin different from 1/2, then ladder operator acting on some component just increase the projection. So this bosonic operator corresponding to the increasing the projection by 1 or spin flip are called magnons. So we find out the excitations in the Heisenberg model at very low temperature. We showed that these excitations are bosons. We call these bosons magnons. And what we have found, the dispersion of these magnons at small q in the long wave limit is proportional to q squared. On next lecture on Wednesday, we will see that there is analogy between Bose-Einstein condensation, superfluidity, and ferromagnetic and antiferromagnetic case. We see in this regard that the dispersion of ferromagnetic magnon is the same as for ideal Bose gas. It's Q squared. We will see that dispersion for antiferromagnetic magnons is linear in Q. It's like acoustic phonons, sound, and therefore it resembles the spectrum of weakly non-ideal Bose gas. So ferromagnets similar to ideal Bose gas, antiferromagnets similar to weakly non-ideal Bose gas. Now let's come to very important discussion.
Sorry, Professor. Hello, you hear me?
Yes, yes.
Yeah, I just missed the point when you talked about the factor of 2 in the structure factor there. When you multiplied with the factor 2.
Because this is 2 times cosine. This is 2 times cosine. This is 2 times cosine. And this is 2 times cosine.
I mean, you talked something like the next neighbor, something like that.
The next neighbors is this. This is 1 over z. As I said, for simple cubic lattice, and I explained you, there are 6 nearest neighbors. If you want to include interaction with the next 2 neighbors, so this will be this one, this will be this one, this will be that one. You will get 12 next to nearest neighbors. This I suggest you to do at home. I, as an example, demonstrate you how it works for simple cubic nearest neighbors. You can take into account next to nearest neighbors and write down, using the definition, you can write down corresponding structure factors. I leave it to you to exercise.
Okay, thank you.
Good.
Hello?
Yes.
Professor? Can you repeat what you said about, I think you said something about J, another J being related to Bose-Einstein condensation and superfluidity.
I told you that the ferromagnetic case has universality class of ideal Bose gas, and antiferromagnets has universality of weakly interacting Bose gas. I will come back to this point on Wednesday.
Okay.
More questions, because now I still have half an hour or less. I want to discuss very important thing. So far, I was talking about Heisenberg model without specifying what is the dimensionality. However, let's do exercise. Namely, let's compute the number of magnons for dimensionality d equal to 3, 1, and 2. So this number of magnons, let me call it n, is equal to sum over q, n, q average. So to be precise, this is a Bose distribution function, sum over q, 1 over e to the power epsilon q over temperature minus 1. Okay? So this is then related to volume integral d q over 2 pi to the power d. I consider d equal to 3, 2, 1. And then it's e to the power epsilon q over temperature minus 1. Again, kb is equal to 1. I'm interested in the behavior of this integral in the lower limit, so in infrared. Because as you know, in condensed matter, there is no ultraviolet divergences because everything is cut by the inverse lattice constant. So d equal to 3. I have integral q squared dq. And as I said, in the infrared, I have inverse size of the system, and the ultraviolet, I have inverse lattice constant. These are limits of integration. And then I will use the infrared limit of my spectrum. Namely, I will take that this is lambda q squared, and moreover, I will expand exponents because I'm interested in the small q. So this is 1 plus lambda q squared over temperature minus 1. Therefore, this is integral dq temperature over lambda squared from 1 minus L to 1 over A. So you see that this integral is not sensitive to the infrared limit. I can take L equal to infinity, and therefore it will give me T divided by lambda, sorry, not lambda squared, lambda A. Okay? So in 3 dimensions, everything is okay. Let's repeat the same in dimension 2. This is integral q dq divided by lambda q squared times divided by t. So this is therefore t over lambda. And I have the same integral from 1 over L to 1 over A dq divided by q. So we see that this is t over lambda log A over L. So the integral, which describes me the number of magnons, is logarithmically divergent with the system size in 2 dimensions. However, it is equal to 0 if temperature is equal to 0. And example number 3, d equal to 1, I have integral dq divided by lambda q squared from 1 over L to 1 over A t. So this is t over lambda times system size. So the number of magnons grows with the system size. What is the conclusion from this exercise? The conclusion is that the long-range order for the system with a short-range interaction is only possible for temperature equal to 0 for 2-dimensional system and is impossible for 1-dimensional system. Basically what happens that the fluctuation grows as a system size and the fluctuations destroy your ordered state. You start with prepared ordered state, but then spins fluctuates, magnons result in a huge fluctuation and the state is destroyed. So in 1-dimensional system, the long-range order is impossible even for temperature equal to 0. So the statement we just formulated now is known as a Mermin-Wagner theorem. And I demonstrated to you on the examples. So in principle, what it says that in 3-dimensional system, we can have a magnetic ordering with a non-zero critical temperature. For 2-dimensional system, the true ordering can only exist at 0 temperature, and in 1-dimensional system, no long-range. Good. If this is okay, I quickly come to discussion of behavior of the ferromagnets at temperatures larger than the critical ones. I remind you that this is magnetization, this is temperature. So now I discussed magnons here, and in the remaining 20 minutes, I would like to discuss what happens if you approach to the critical temperature from above. Yes?
Sorry. I don't get your point when you're discussing at that 1 dimension about the how is it diverging and it cannot exist exactly.
I computed the number of magnons in the system, and I see that the number of magnons is divergent. It's simple exercise in principle. In principle, true calculation is more complicated. In principle, I need to compute density-density correlation function. And we will repeat it when we discuss antiferromagnets. Because for antiferromagnets, the simple arguments, one needs to use more sophisticated arguments. For ferromagnets, even simple arguments, like computing number of magnons and see that this number is divergent, is enough to say that there is no long-range order.
So since it diverges with the system size, you cannot have long range order because of that divergence.
Yeah, because the number of magnons scales with the system size. Yes, and for 3 dimension, it is not sensitive to system size. You can send your system size to infinity, take thermodynamic limit, and you get final result. Here, the number of magnons grows linearly with the system size. For 2-dimensional system, it grows logarithmically, but luckily there is a coefficient temperature which controls this behavior. So if temperature is equal to 0, despite the logarithmical growing of the number of magnons, it is cut. So it is actually nullified by 0 temperature. Okay. Can I move on?
I have another question. For the for example, how you actually apply the mean field for the Heisenberg model? I mean, is it like you need to replace everything from the beginning, or you just need to do it at the last part?
Well, as I said, I started to say this, but you interrupted me. So I said that I begin with a description of behavior of ferromagnet at very low temperature. Temperature is much lower than this. Then what happens if you increase temperature? You go along the curve, and you see that curve actually is quite close to 1 for close to its value at 0 temperature. The deviation is exponential. This is what you did with Andrei when we discussed the superconductivity. This is the same sort of Mill equation, so the deviation with temperature here is exponential. However, if you go down, 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 the validity of your Mill theory becomes less and less, and you need to do something else. Moreover, I should say that I defined the spectrum. In order to say that magnons are true excitations, I also need to discuss the lifetime. The lifetime of magnons is determined by magnon-magnon interaction. This is what I dropped from the Hamiltonian. What I need to do in order to discuss the inverse lifetime, I need to restore terms which is proportional force power of creation and annihilation operators. And I need to compute then the decay of your excitations. It's quite a complicated problem. However, if you do that, you will get that inverse lifetime at small q is proportional to q to the fourth power. And this is a good sign because spectrum is proportional q squared, inverse lifetime is proportional q to the 4. So as long as you are in the long wave limit, magnons are well defined the occurrence. However, in the vicinity of critical temperature, magnon-magnon interactions become stronger, and you have less and less defined magnons, because temperature also comes into the consideration. The theory, full-fledged theory of quantum ferromagnets at arbitrary temperature goes far beyond the topic of my course. If you are interested, you can read it in some books. Moreover, for two-dimensional system, you see that the phase transition occurs at 0 temperature, and this is so-called quantum phase transition. What we see in all examples before, that the phase transition, this is a 3-dimensional case, is driven by temperature fluctuations. And if you are at 0 temperature, the phase transition is driven by the uncertainty principle, Heisenberg uncertainty principle. So this is completely different type of the phase transition in a sense. And since it is related to Heisenberg uncertainty principle, it is called quantum. So there is a lot of interesting questions to discuss here. I simply don't have time. I'm giving you some basic information without which you probably cannot live as condensed matter theorist, but the rest is up to you to read books, to read papers, and to understand what's going on. Quantum phase transition is a very hot topic for a recent, let me say, 15 years, because it seems to be relevant to what's going on in high temperature superconductors, and there are many, many other realizations of this quantum phase transition in the literature. Okay, let me move on. Okay. So since I have less time, I leave you something for homework to read it, but let me make some statement, just sketching derivation. You will do the derivation by yourself. So above TC. Above TC. Above TC, I have a paramagnetic state. Let me take some non-uniform magnetic field. So what I will do is the same trick which I discussed introducing it to random phase approximation. I will introduce non-uniform magnetic field, picking some component Q node. So monochromatic waves with a momentum equal to Q node. So H, which is H external, is equal to H Z times cosine Q node R. It means that I'm applying field something like that. So it's oscillating with a certain period related to Q node. And I'm writing my longitudinal part of the Hamiltonian, which is minus G mu bar H times sum over n S and Z, and I have a cosine Q node R. So since cosine is sum of two exponents, so this is minus 1/2 G mu bar H. So I have S Z Q node plus S Z minus Q node. Okay? So this is a probing field which I'm applying to my system at the temperatures slightly above critical temperature. So since I'm in the paramagnetic phase, my magnetization or the moment spin which I induce is proportional to magnetic field. There is no spontaneous magnetization. I'm in the paramagnetic phase. So this is a ferromagnetic phase. This is a paramagnetic phase. So in paramagnetic phase, I can write down my mean field Hamiltonian in a way. Mean field means I replaced in the Heisenberg Hamiltonian. So Heisenberg Hamiltonian is sum J and M S and S M. I will call it HH because this is external magnetic field plus HH. So what I will do here, so this is, by the way, if I apply Fourier transform, sum over Q, G, Q, S, Q, S minus Q. Here, what I said, I'm applying conventional Fourier transform. Let me write you down here that S n is equal to 1 over n sum over Q SQ IQ Rn. You see that instead of doing symmetric, that SQ will not contain factor n. It's a sum over n, SQ, Sn, sorry, e to the power minus IQ Rn. So I'm not symmetrizing. I'm not putting factor 1 over square root. And I'm not using different Qs for ladder operators, because I don't need ladder operators now. There is nothing like creation and annihilation. So this is another convention. Please pay attention. So what I said, that in this Hamiltonian, I will apply mean field, therefore I will replace one of the spins by its mean field value. So I will rewrite this Hamiltonian is JQ node, because I'm interested, only one component, Q node, is activated. So if I take SZ Q node, SZ Q node minus Q node, minus Q node SZ Q node SZ minus Q node. So I just first replace it by averaging first term, and then I replace it by averaging of the second term. Again, I use the fact that only magnetization along Z exists. So this is where magnetic field is directed, is not equal to 0. And then I have minus 1/2 G mu bar H times SZ Q node plus SZ minus Q node. This is the mean field Hamiltonian. And this Hamiltonian resembles me the Hamiltonian of spin in some effective magnetic field. You see that this contributes to effective magnetic field, and this contributes to effective magnetic field acting to the minus Q node, and so on and so forth. So now I have two fields in my system. First one is external magnetic field, which I denote as H. And then I have effective magnetic field, what I called gamma in the first lecture, which is associated with the fact that all other spins interact with a given spin. This, by the way, gives me connection between gamma, phenomenological parameter, which I introduced on the first lecture, and the microscopic parameter of the model. So then, if I compute susceptibility, by the definition, first of all, chi node is the limit of mz depending on Q node divided by H effective. H effective goes to 0. Mz Q node is equal to G mu bar SZ Q node plus SZ minus Q node by the definition. And HQ is the limit of H goes to 0, namely external magnetic field goes to 0, mz Q node divided by H. So this is what leads to Curie, and this is what leads to Curie Weiss. The only difference is that I see the Q dependence. So I take into account fluctuations. If I write down from the first equation that mz is equal to chi node times H effective, and if I take out H effective from my Hamiltonian, I can write it down as GQ node over G mu bar chi node times volume times SZ minus Q node plus 1/2 H V chi naught. This is from this term. As a result, since I take into account Q naught and minus Q naught component, at the same time, this is chi Q times H. Therefore, I obtain that chi Q is equal to H V chi naught divided by 1 minus G Q naught. It's Q naught. Chi naught V divided by G mu Bohr square. So this is, sorry, this is magnetization, sorry. If I divide, I get H cancelled out from the numerator. Okay, now I'm saying that I selected particular Q node, but let me now replace Q node by arbitrary Q. This is the spirit of random phase approximation. This is what we did for Coulomb interaction. And I'm writing that chi Q, if I divide by the number of spins, it's equal to G mu Bohr square S plus 1 over 3t divided by 1 minus G Q times N times S plus 1 over 3. Here I use the fact that chi naught is equal to, this is what we got in the first lecture, to revise. It doesn't depend on parameter gamma, G mu Bohr, S plus 1 over 3t. This is Q. And this is Q revised. So far, so good. So what remains is to write down the susceptibility at small q. I will define the critical temperature the same way as I did it on the first lecture. Consider the quantum part. This is Z, G, S plus 1 over 3. Remember, I set a connection between gamma and my microscopic parameter J. And therefore, for simple cubic lattice, I have chi Q goes to 0 is equal to C over Tc. 1 T minus Tc over Tc plus Q squared A squared over 6. This is C. Oh, with a 3. Good. So, without this term, namely if Q is equal to 0, we reproduce what we obtained through the molecular field theory. However, now we include the small q into consideration. Therefore, we included the fluctuations associated with existence of different moments. I remind you that this parameter is tau, I can write down my susceptibility Q goes to 0 as some constant divided by tau plus Q squared A squared over 6, or this is Q squared plus kappa squared, where kappa squared is equal to 6 tau divided by A squared. So kappa has a dimension of inverse length. Tau is a dimensionless parameter. Tau is T minus Tc over Tc. Therefore, I can introduce correlation length, which is A divided square root over 6 tau. This is a correlation length. The same way as we introduced correlation length in the theory of superconductivity. What we see here, that the correlation length is divergent as a 1 over square root of tau when you approach the critical temperature. If we now compute the Fourier transform of this function, by the way, this form is called Einstein-Zernicke. If we compute Fourier transform of this correlation function, assuming that the form of it survives also for large Q, we extend this definition for large Q, we obtain that chi r, this is the same shape as screened Coulomb interaction, chi r is proportional e to the power minus r divided by psi divided by r. This is last comment which I would like to make. Physically, what happens? You are at temperatures above critical one. You are in a paramagnetic phase. However, you low down your temperature such a way that you approach to the critical point. You are considering model with a short range interaction, namely only nearest neighbors interact. However, you see that by approaching the critical temperature, your spins start to be correlated with the correlation length, which is inversely proportional to the small parameter which describes the closeness to the phase transition point. More you're approaching, the larger correlation length is going to be. So when you approach to a critical temperature such a way that your correlation length becomes comparable with the size of the system, the long range order is established. So this is a mechanism of establishing of the long range order in the system when you approach to the second order phase transition point from above. So this is the meaning of this exercise. Okay, if you deviate, slightly deviate from the temperature, then you have only short range orders. Some spins are correlated, but the correlation length is very much limited. Only when you come closer to the phase transition point, actually all spins fill the area of the size of the correlation length. Okay, since there were many questions, I planned to give you more details of the calculation of the Einstein-Zernicke. However, I sketched all steps. This particular derivation can be found in a white book, which is called Quantum Theory of Magnetism. So those who would like to understand more and read more details, I refer to the book of White. However, I should confess that personally, I don't know any book which is particularly good for theory of magnetism. It's either very special and contain many details which are probably not necessary for the first acquaintance, or addressing some another particular things like experimental observation. So yeah, the best book for the purposes of today's lecture is book of White, for the second part of today's lecture. Good. Any more questions? On Wednesday, we will get through the description of antiferromagnetic magnons at low temperature, and then I see if I have more time, I will probably go along the lines of the same derivation for the antiferromagnets, so deriving Einstein-Zernicke theory, or we will have time to discuss some strongly correlated models like Conde model, Stoner model, Hubbard model. Let's see. Because Wednesday lecture is the last lecture, given with the Blackboard. On Friday, I will show you some slides related to summary of superconductivity and magnetism, including theory of high temperature superconductors, present state of theory of high temperature superconductors and heavy thermal compounds, but it's going to be given with slides. Wednesday is the last Blackboard